Sure, you don't have to go with full-on colors here. I think I will, just to maybe make it a little bit easier to see, at least for me. So here is the ocean right here. And the sand, we're going to make it, I don't really have a brown. Well, I'm going with brown. I'm going to go with kind of a brown. Pink sand, that does sound cool, but good idea. Okay, so the guy is in the water like right about there. And it says that he is 2 miles from the nearest point of land. So, how about that? Would be 2. Does that make sense? Okay. And he wants to get to point Q, which is located 3 miles down the coast and 1 mile inland. And so we'll say that point Q is right about there. And then that would make this distance 1 mile. Okay. So then the whole distance right there, that would be 3, wouldn't it? So that would be 3. So then this is where we kind of, hey, Lenny, this is...
a little late.
That's okay. So this is where we kind of have to start understanding the content of the question, because if the question said, and this is where, Sean, we can clear up that question you had a second ago. If the question said, in what direction should this person row to minimize distance, wouldn't they go straight at Q on a diagonal?
Yes.
That would truly minimize the distance, wouldn't it? And if this guy could row and walk at the same speed, then the minimizing the time and the distance would be one and the same.
Yeah.
But the truth is, he rows and walks at different speeds, which I think we understand. It's much harder to row in the ocean or a lake or whatever than it is to walk. And so he's slower in the water. And so he needs to essentially, he needs to paddle in the water, obviously, but he doesn't want to do too much of that, right? Because he's slow in the water. We're going to find that if he were to go straight at the coast, that actually, because you might think, hey, why didn't he just go straight, like to truly minimize his time in the water? And then, just walk on a diagonal to Q. We'll find that that's pretty close to minimizing his time, but it doesn't. We'll find, that's logical. I totally get that. We're going to find that he needs to go at kind of an angle. Well, maybe a little steeper, who knows. Something like that, and then something like that. So it's going to be 2 triangles, for sure, 2 different triangles. And logically, hopefully it makes sense that he would, spend a little more time on the land because he's faster on the land than he would in the water. And then as far as the picture goes, or labeling the picture goes, goodness, I'm going to try to get this right. There we go. We'll call it good. We know that whole long horizontal line is 3 miles. We don't know where he's going to hit the coast. So would it be okay if we all called this X, that little short base of that little triangle? And then if that's the case, then what would be the length of the other triangle's base? 3 minus X. Okay. So it'd be nice if we could all agree that that's the picture we'll go off of, so that maybe our later steps will kind of go together somewhat. So let's start right there with that picture and see if you guys can now kind of get to work on, all right, how do we get an expression for time, and then how do we minimize it? Okay, so I'll let you guys kind of take over again for a couple minutes and see where we questions for times. So I think what we would do here is say that we go back to Algebra 1, really. Say that distance is equal to rate times time.
Plus or minus 2.
Make sense? Okay, so then we could say that the distance in the water divided by the rate in the water, so that's 2, is equal to the time in the water. And then we could also say that the distance on land divided by 4 is equal to the time on the land. So then the overall time that we're trying to minimize, wouldn't that equal those 2 times added together? So I would say that's equal to dw over 2 plus dl over 4. So now we're getting into some details here that we can start to use a little bit. How would we figure out the distance in the water or the land? Pythagorean theorem, or you could use the distance formula, right? It's the same thing. So we could then say distance is equal to, I'll write it as 1/2, or excuse me, time equals 1/2. Distance in the water would just be x squared, square root of x squared plus 4, plus 1/4. Distance on the land, let's see here, that would be 9 minus 6x plus x squared. Did I mess something up?
Is this a distance formula?
It is.
Okay, good. Don't know.
So 10 minus, or Pythagorean theorem. I am skipping a step. I'm adding the 1 onto that right away. Did I do my math right? 9 minus 6x plus x squared plus 1 more. So you'd add the 1 to the 9 and get the 10. Does that make sense?
Yes.
So that would be the time, like that would be an expression for time. So if you wanted to really talk about what this part means, you could say, well, if this guy rows to a point on the shore, like maybe if x is 1, then wouldn't you just plug a 1 in for x, do some arithmetic, and that would tell you the total time, right?
Yeah.
If you wanted x to be 2, follow the same procedure, just plug in a 2. Say again? And we want to try to find the minimum for time. And so obviously we don't know that that's going to be a nice integer value. In fact, we know that likely it won't be. And so we need to use the derivative in order to try to minimize that time. So this is where you'd find t prime. Sean was doing something with this, and he's like, can we use the calculator to find the zeros? Yes, you can. So find t prime, set it equal to 0. Use your calculator to find critical numbers. And then you could also then use your calculator to hopefully confirm that that critical number generates a min. So give it a shot. I will quietly calculate a derivative up here. The real challenge might be making sure you get that entered into your calculator accurately. Once you do that, you should be in pretty good shape.
Good luck with
The
that.
real challenge.
And so do we have a consensus that yes, x equals 1 is the critical number?
Yeah.
The consensus. Okay, so if you solve that equation via the calculator, you get x is equal to 1. So then, toward what point on the coast should he row? How would you describe that? You could say, if you've got your picture there and you say, okay, x is 1, that's a pretty good description, right? If you didn't have a picture, you'd have to say, 1 mile down the coast from his nearest point to the coast or something like that. You'd have to use some words. But in this case, I think a picture is worth a lot of words, and so I think it would suffice to have that picture along with your answer. Okay, so was that kind of fun? It was just out there, right? Kind of a different question. It's not quite so cookie cutter like some of the other questions we see. I hope you enjoyed that. You guys had some really good discussion. Get that figured out. So any follow-up questions of any kind? Yeah, McKenna, go ahead.
Are the answers to the practice posted?
They should be, yeah. If they aren't, let me know. I feel like I got all those covered, but every now and then I feel like maybe I forgot to upload something. So they should be in there. Should be. Okay, so we good? Okay, fair enough. Let's move on then to our final section in here, 3.9. There you are. Okay. So this gets into using tangent lines that we've talked last year, and I guess we really haven't talked a whole lot this year yet about finding tangent lines, but last year, I know at least in my 2 A-B sections, it was a major focus, and we talked a lot about it, or a lot of questions at least were asked about it. So this will be a nice review for us. So the tangent line is a really good approximation for values that are close to what? Point of tangency, yeah. So if you're really close to that point of tangency, then your approximations tend to be all right. The further away you get, the worse they get. And believe it or not, later on this year, second semester, I'm using improper terminology here, but we will start looking, instead of at tangent lines, almost like at tangent curves, kind of, sort of. We'll call them different things than that, but we'll be able to improve the accuracy a lot by doing that, as you can well imagine. But we're going to stay with tangent lines for the moment here. So for the function f of x equals root x, let's practice. Let's find the equation of the tangent line at the point of tangency 2 comma root 2. So I'll just ask you, what are the two things you got to have to find the equation of a line?
Points and slope.
Point and a slope. And so specifically for a tangent line, we want the point of tangency, which we've got right there. And then we want the slope of the tangent line. So again, I'll let you kind of run through this. Let's see how much of this you can do. It is all review, so you might be able to just do it no problem. If not, we'll do it together here in a little bit. Hey, let's review, see what this tangent line equation should be. We already have the point of tangency, so we just need the slope of the tangent line. So we want to find our first derivative. So f prime is equal to 1/2 x to the negative 1/2. So we want to know what f prime of 2 is. So that would be 1/2 times 2 to the negative 1/2. We could flip that down and maybe rewrite it as f prime of 2 equals 1 over 2 square root of 2. You could do that obviously in a variety of ways, but that would be a good way to do it. So that's our slope of the tangent line because that's the value of the derivative at the point of tangency. So we can then write our equation of the tangent line. It'd be y minus root 2, we're using point slope here, equals 1 over 2 root 2 times x minus 2. And I would, to be honest with you, Sean, I noticed that you were like put some effort into going to slope-intercept form. I would just leave it like that. That is an equation of the tangent line. And it didn't say anything about point slope or slope-intercept or general or there's another form. I didn't say what form, so we could just use whatever's easiest for us. So I'd leave it like that. Is that all okay? Okay. Part B, so then using that to approximate the curve, what we would do is take that 1.8 and we'd plug it in for x. So still haven't had to touch the calculator yet. I don't know if we have to, unless we want to get a good approximation. So let's see here, 2 root 2, this would be 1.8 minus 2. Let's plug in that 1.8 in for x. So 1.8 minus 2 is negative 0.2, and this would maybe be where it gets a little ugly without a calculator. You could, let's see here, 0.2 is 2/10. So this would be negative 2/10, so it'd be negative 1 over 10 root 2. And then you'd add, so you'd get y equals negative 1 over 10 root 2 plus root 2. I hope I did my arithmetic right there. What'd you get for a decimal? 1.3435. So I'll go with 344. And then we can...
Human lives are at stake.
What's that?
Human lives are at stake. We can't round to 2 decimals.
Ooh, wow, okay. Well, I didn't realize that. So 3.5 for the sake of human lives. Going with that. So approximately f of 1.8 would be what we would represent there. Okay. So, of course, what we're doing is we are saying that we've got this curve. We know that that graph of that square root of x function looks something like that. And then our tangent line would look roughly like this. That came out all right. And so, you know, the point of tangency would be right there. And so right there at the point of tangency, of course, the slope of the curve and the slope of the line match, right? And the xy on the line and the xy on the curve match. As soon as you start moving off of that point of tangency, things don't match anymore. And so 1.8, of course, is to the left of 2. So 1.8 would be over here somewhere. So we can see that when x is 1.8, the line is slightly above the curve. So we can see that it's an approximation, is truly an approximation. It's not exact. And so we can see from the graph that, yeah, the line's a little too high compared to the curve, right? Does that make sense? Okay. Any questions so far on A and B? So C says, is the approximation from part B too high or too low? Why? So you'll be kind of pinned down on this one on a quiz or a test as far as what you could use to prove why. So here, if you were to say, hey, I graphed it and I see that the line's above the curve everywhere except the point of tangency, that would not typically be something that would be in the okay place for justification. Usually it'll say, justify yourself using like a second derivative or something like that. So that's what we'll do here. So did you guys all use a second derivative kind of a thing? That's what we want to do, and it could lead to concavity, and then we can get there eventually.
Have McKenna Baldwin come to the front desk for an appointment, please.
Okay. All right, so we end up with, let's see here, f double prime of x is equal to negative 1/4 x to the negative 3/2. She's on her way. And so we are interested in this the value of the second derivative technically on the interval from 1.8 to 2. We want to make sure that that it's got a consistent second derivative value there. So let's see here. I'll rewrite it. Is that it for today? You gone?
Yeah.
Okay. Have a good day.
Thank you.
See you next week. So I'll write it as something like negative 1/4x to the 3/2. And this is where we can just do some analysis in our brains, right? We don't have to write a whole lot of this down. Let's think how this is going to go. We know that the domain for f of x is 0 and up, right? 0 to infinity. And so any number we plug in for x has to be what?
Positive.
Got to be positive, right? Okay, so if all the inputs have to be positive, then we do positive number to the 3/2 is going to be positive, times 4 is going to be positive, and then all of that under -1 guaranteed has to be negative. So this will be negative for all of the domain. All right, so we could say I suppose you could do this in one of two ways. You could say for this interval here, 0 to infinity, that would cover it, or you could say, more applicable to this question, 1.8 to 2. So one of those 2 points in your interval has to be the point of tangency, and the other one has to be the point that you plugged in. So we can, sorry, that's right on the thing there, isn't it? I should have planned that a little bit better. Is that readable at all? Understandable since I said it? Is that okay? I guess you could go back and watch the video because the video doesn't have that thing in it. Anyway, so we know for sure that the second derivative is going to be negative regardless of where we are on the domain. Therefore, f, I'll put this up here, therefore f is concave what? Down. And then you can then use that kind of reasoning along with knowing what the graph looks like and say, okay, well then for sure my approximation is too high. So therefore the approximation is too high. Okay, so that's kind of reasoning we'd want to see. You guys all comfortable with that from last year? Sean, does that make sense to you? Okay. All right, awesome. So let me just ask you one quick thing here before it says find the equation of the tangent line. I put this in here because we all got to be good at the unit circle, right? So it's like, let's take another opportunity here to make sure that the unit circle is not going to be the issue. And make sure you can do the stuff that you should be able to do without a calculator. Calculator will come in handy here at times, but like when you got to do sine of 5 pi over 4, don't do your calculator, right? Just a thought. Yeah, other times you need it, but for stuff like that, try it without. All right, so you can see same set of questions, just a different function. Give it a shot. Okay, so I'm going to get rolling on this one.
For your second derivative? Carolyn, did you get it was too low?
Yeah.
Okay.
So 2 cosine of 2x for g prime. So g prime of 5 pi over 8 would be 2 cosine of 5 pi over 4. And cosine of 5 pi over 4 is negative 1 over root 2. Did you guys get negative 2 over root 2 for a slope of tangent line? Make sense? Negative 2 over root 2 for your tangent line slope?
Yeah. Yes.
Okay. Okay, yeah, no worries. All right, so then your equation of tangent line would be y minus minus, so it would really be plus 2, or excuse me, root 2 over 2 is equal to negative 2 over root 2 times x minus 5 pi over 8. Okay, a little on the ugly side there, but you know, it is what it is. It's it's accurate, so we're good. Happy with that? Okay. So then in B, this is obviously where the calculator would come in handy. We'll just plug that in. So y plus root 2 over 2 equals negative 2 over root 2 times 2.1 minus 5 pi over 8. So would you guys mind sharing what you got for the y value once you solved it?
Negative 0.900.
Negative 0.900. Okay. So then we'd say that that's approximately equal to g of 2.1. Okay, so I'm hoping that A and B, it was a matter of, maybe it took some effort, but you just had to kind of get it done and you could do it okay. C, like I said, this is always kind of the challenging part. We want to determine is the approximation that we just found too high or too low. And so we want to use the second derivative to do that. So the second derivative for us in this case would be g double prime, and that would equal negative 4 sine of 2x. So then here is where it gets tempting to get a little lazy and not do your due diligence as to what you're supposed to do. Here's where it's tempting to, you found your g double prime just fine. It would be tempting to take 2.1 and just plug it in, right? Or 5 pi over 8 maybe and just plug it in. But what we need to do is make sure that that whole interval, g double prime is either positive or negative, whatever it is. We want to make sure it's consistent. So in other words, we don't want g double prime to change signs right in the middle of that interval. So it might be nice to find out where g double prime is 0, because that would give us a hint about where it might change signs. So I'm going to set this equal to 0. And dividing through by negative 4, I get sine of 2x is equal to 0. So 2x is equal to inverse sine of 0. And this is where our unit circle skills make it nice. Or if you had the calculator, you could totally cheat. Anyway, inverse sine of 0 is 0. And pi and 2 pi and all those, right? So 0, pi, 2 pi, 3 pi, dot, dot, dot. Hopefully that's far enough. That's equal to 2x. You divide everything through by 2, you get 0, pi over 2, pi, 3 pi over 2, etc., etc. Dot, dot, dot kind of showed up there. Okay, so then let's analyze this. 5 pi over 8 is in between which two values?
Pi and 3 pi over 2.
Pi over 2 and pi.
I think it's pi over 2 and pi, right? So 5 pi over 8 is like 5/8 pi, and 5/8 is just a little bigger than 1/2, but it's definitely smaller than 1. Okay, so then, so that fit between pi over 2 and pi. What about the 2.1? Does that fit in the same interval? Yeah, so because pi over 2 is like about 1.5, and pi is 3.14-ish, so 2.1 does fit in there. If you had 5 pi over 8 between two numbers, and then 2.1 was in between two other numbers, then I wrote a bad question, or we just wouldn't really be able to answer this, at least based on the second derivative. So they are both within pi over 2 and pi. So that means we can just plug one of them in, and that'll help us. Or you could plug whatever you want in, to be honest with you, as long as it's within that interval. So we could just go g double prime of, you know what, I'm just going to do, 5 pi over 8. That'll tell us what we want to know. So that would be sine of 5 pi over 4. So that would be negative 1 over root 2. So times negative 4 would be positive 4 over root 2. So a positive number. So then we can say this. We can say that g double prime is positive on the interval from, let's see here. What's bigger, 5 pi over 8 or 2.1? I'm honestly asking. I don't know. Can you help me out? So 5/8.
2.1 is bigger.
2.1 is bigger? Okay. So 5 pi over 8 to 2.1. So if g double prime is positive on that interval, that means that g is concave up, which means that our approximating line is too low. So we can say, therefore, the approximation we found is too low. Sorry, that kind of went off the edge there. All right, so did you guys come up with a similar idea, similar strategy? Did it work for you? Do you have any questions? I'm trying to treat you like the honestly, like the good students and scholars and math people that you are. I feel like you're doing well. Yeah.
How many points would you get off if you didn't prove that they were in the same interval, like 2.1, like they were?
Yeah, good question. So, I think probably if this were a quiz or something, I'd probably make C a 2-point question. 1 point would be too low, right? But I would tie to that like some kind of a logical reason. So I'd say, 1 point is too low. 2nd point is, the correct reasoning. So like if you messed up the reasoning somehow, maybe it'd be 1 out of 2 possibly. But if you just put like too low with no reasoning at all, I'd have to think about it. That might be considered a bald answer, right? Because it truly is a coin toss, too high or too low. So I'd want to see like some attempt at reasoning with that. So, probably like if I saw that you made an attempt, but you like didn't really get the interval, but you found a value for g double prime that maybe was applicable, maybe go like 1.5 out of 2 or something like that, because it shows you understand, but not like all the way. So yeah. All right, good question. Hey, I just want to point out kind of our last little bit here. We're not going to do a whole lot with it. The last little piece here just has to do with differentials, and this is more, we're not going to do examples 3 or 4. They are pretty interesting. If we do have time, we might come back and talk about them, but they're not necessary. But I do want to just mention this because it leads us into chapter 4 a little bit. If you remember, who was the guy that came up with this notation on the left? German guy, Leibniz. Good memory. And then who was the person that came up with the other notation? Newton, right. So if you take that equation and you write it, you multiply through by dx, you get dy equals f prime of x times dx. And so we would call dy the differential of y, we'd call dx the differential of x. And often those are just like, short referenced as just the differential, Like we'd call dx, like if we're doing an integral later on, we'd call dx, oh, you forgot to put your differential on there, that kind of thing. Just so you know, that's just a reminder as to where that comes from, and it can be used to do some interesting things. You can also do the same thing with tangent lines. So just thought I'd mention that to you. That's it for chapter 3. So